Welcome to another session of the Network Cellular Series, hosted by the Center for Network Intelligence at IISc and RVC's EPS IISc. Be Arvind Rameshwar, and he will be speaking on coding schemes for input-constrained channels. Arvind Rameshwar received his BA in Electronics and Communication Engineering from Bangalore University 2018. He is currently pursuing his PhD at Department of ECE IISc Bangalore. He is recipient of the PMR 2020 and was part of the team that won Quantum Innovation Fellowships India 2020 and 2022. His papers co-authored with his advisor have won student paper awards at the NCC 2021 and IEEE International Conference on STCOM 2022. His research interests lie in information theory and coding for channels with memory. Before we move on to the talk, we request the online audience to please keep your microphones on silent for the duration of the talk, except when asking questions. And for asking questions, you may unmute yourself and ask Arvind directly. Over to you, Arvind.
Thank you all for coming firstly. I hope this is audible. Is there any way of checking whether the mic is working?
Fine. No, it's not working. Try to increase the volume. It's working. It's working.
Cool. So the title of this talk is Coding Schemes for Input Constrained Channels. And all of what is going to be presented here is joint work with my advisor, Professor Reed-Muller at IISc. In this talk, we'll be seeing certain very specific things at the outset. And then we'll gradually try to make things more general as the talk progresses. There are many very lofty goals that we are trying to address in this talk. We'll see how much progress we can make as we go. So we are broadly interested in the design of coding schemes over certain channels that look like this. So we have a message that is required to be sent that's chosen from a certain message set. Now, an encoder encodes this message into a binary input sequence xn, and this input sequence is sent over a channel. We get an output sequence yn, which is then decoded by the decoder to get some estimate and back to the original message. So this is the recurring broad channel model that will be used throughout. Now, what does this channel look like? This is a channel with memory, in the sense that the channel has a certain parameter called a state. And this state, Si, at any time I, takes one in infinitely many values. And the transitions between the states of the channels are possibly driven by inputs. They could even happen independent of the inputs, but that is a channel model that we will not be interested in for the focus. There are very many channels that are well modeled by such.
Sorry, we're trying to switch off the light.
Yeah.
We switched off something else. I mean, switched off projector.
So yeah, we were speaking about the kinds of channels that we'll be discussing in this talk. This is the channel with memory, as I pointed out. And examples of such channels include intersymbol interference or IISc channel models for GECs, input constraint channels, and so on. And for the purposes of this talk, we will restrict our attention to input constraint channels. What are these channels, and what are the sorts of input constraints that we'll be dealing with?
Sorry, one. So this, yeah. Every channel has a state, right? It's just that this IID won't care about this. Right? I mean, they're just trying to understand because I hear this terminology and I'm not able to make sense.
Yeah. So in the event that the channel is memoryless, you just have the state taking a single value, like a singleton state space is a singleton.
No, state space is not. State space is all possible states you can take. So even if say IID channel, right, you could possibly be good, bad, ugly, whatever, right? All possible states. It's just that every time the probability, distribution of the states, this remains same. It is not driven by what the input was. Or
oh, you're calling that an IID channel?
I mean, okay. So what do you call IID channel? To me, IID is something which is the realization of the channel does not depend on the pass. Right?
Sure. So I guess those kinds of channels are sometimes called as arbitrarily varying channels, so AVCs, where the state process is IID.
Sorry, just trying to get terminology.
Yeah, sure.
And here, what do you call IID then?
When I mean an IID channel, in some sense, can be thought of as a memoryless channel or DMC, where there is literally no state, or the state space is just a singleton, it's just one state, and the channel output at any time is just a stochastic function.
So it's a bit not completely clear, right? So because even if you think of discrete memoryless channel, right? It's not. I mean, are you thinking that epsilon is your state? But really, state means that if you give me xi, the yi could be xi or it's complete, right?
The xi of some stochastic function of xi.
Right, correct. Yes.
Right. So the state there is just.
But actually, you say stochastic function. That means my output has a distribution over all possible. And there is a distribution over complete output.
Yeah, there is even no. Okay. So condition on the input, there is no distribution.
Correct. Exactly. Right. So,
now, when we talk about a channel,
what is the singleton for you? For me, the state space is exactly all possible values the output can take. Right?
well, the state space for me is a state in which the channel resides at d time. So the output then is a stochastic function of both the input and the state in which it resides. Okay, so it's like P of yi given xi comma s. Okay. And here si for DMC is just a single.
Okay. The memory of channel is like what do we mean by memory of channel? Like these states, they will be depend on the previous time.
Right. So the states could potentially, yeah. So the memory of a channel, very loosely speaking, is the amount of time you need to wait before the channel loses track of its initial state.
I think best if you give the example of Gilbert, the memory is like right there.
Yeah. Okay. But
okay, fine.
yeah. So I mean, you can construct, say, a finite state machine, okay, which represents the transitions between states, and you can look at the memory of this finite state machine in any well-defined sense, which is just going to be something like the longest time you of the
No, but it's vague. I think maybe what you want to. I mean, I don't know. I think that if you have Markov channel, then the memory is very different, right? Then you're talking about mixing times.
That's right. Yes. So if you have a Markov channel, for example, the Gilbert-Elliott channel, it's a Markov channel where the transitions between states are Markovian. Then really the memory of the channel is it's a first order Markov memory. Then you can have channels with larger memory. They need not necessarily be. They need not have 2 power the memory of number of states. The memory in that case, you just define it as the length of time you need to wait till it basically forgets the initial state. This can be made rigorous, but I don't wish to because this talk is not going to. Okay. So what is the goal of this talk? Broadly speaking, we are interested in designing coding schemes over such channels of memory, and in particular over input constraints.
So one more thing that I heard part of it before. So when you say input constraint channel, what I remember is that your inputs are constrained to come from a set, right? But how is channel? You're saying that channel is forcing you to be in certain states?
Yeah. So the channel requires the inputs to belong to a certain set.
So this it's not clear what the input constraints have to do with memory. They have to separate things.
Yeah. So you can cast the input constraint as a channel movement. So if you look at an input constraint channel, you can think of it as a channel movement. So if you have an input constraint acting before, say, a memoryless channel, then you can put a box around the entire encoder plus channel and define a channel with finite alignment steps. Okay, so all of this is going to lie within the edges of finite steps. Okay, so just to go one step deeper, there are two kinds of settings or channel models that we'll again be looking at. The first is the case when you have random noise affecting your code.
So is it possible that above or okay. Not stop sharing this?
Should go.
There is a height meeting.
It's
So
fine.
It's fine.
This is fine.
Height floating.
Height meeting.
Okay, so the first case is the random noise channel model, which we are all very used to in information. And the second one is what coding theorists primarily work with, which is the adversarial noise model. What is this channel model? When you have an encoder, constraint encoder, which is going to produce constraint inputs, and the channel is allowed to introduce errors with potential knowledge of the code word that is meant to be sent. Okay, so the only caveat is that there is an upper bound on the number of errors that this channel. Unlike in this case, where the noise is introduced random fashion, which means that the noise correcting a particular input symbol has nothing to do with the noise correcting another input symbol. Again, you have a constraint encoder here. And the kinds of constraint sequences that we'll be looking at find application in a lot of areas. Recently in DNA storage, in energy harvesting, wireless communication, and traditionally in magneto-optical recording, flash drives, drives. So what are some of the constraints that we'll be interested in? The first is the so-called class of run-length-limited constraints. And these are constraints that have traditionally been used to alleviate intersymbol interference in magnetic. Then we have subblock composition constraints. These are constraints basically which require that the signal power in any subblock in your input sequence has to be at least so much. And this ensures that the receiver battery doesn't drain out during low signal levels. And finally, we'll be looking at certain charge constraints. And these are constraints that have, again, been introduced in the past in order to ensure that the input frequency spectrum has certain spectral noise. So let's look at what we'll be covering in this talk. This talk has two parts. Firstly, we'll be designing explicit coding schemes for certain very specific channel models, keeping in mind that the channel introduces random noise. And this is the first part of it. Now, in part A, we will be dealing with a very specific constraint. And we'll be trying to use the learnings from part A in order to generalize and come up with recipes for counting constraint code words in general linear groups. And in part 2, we'll be looking at the second channel model, which is that of the adversarial channel. And we'll see if we can derive good bounds on the sizes of constraint codes that can be sent over such channels with a given error tolerance.
So since you seem like you only care about counting the possible inputs, right? And how does that happen?
Not in the ambient space, but in any particular linear code that you use. Okay. So why is this so? If you have a random noise channel, it's very well known that there are a lot of linear codes that perform really well in the context of.
No, this is fine with you, but why is this counting important? That's all I'm asking. You're saying
Counting gives you the rate.
it's true, right? But then it does not say anything about the error per se. For example, that
Since it's a linear code, subcodes will have the same, will behave the same way as far as vanishing error properties are in the limit of clock and going. We'll come back to this point. So let's look at the first part, which is about input constraint symmetric random noise. So just to rehash, you have a symmetric channel sitting in the middle there, which is called BMS channel, the binary memoryless symmetric channel. And you have a constraint encoder that's going to send constraint sequences over this channel. And common examples of such BMS channels include the binary erasure channel, we all know the binary symmetric. There are many others, the binary AWGN channels.
So what do you call state here?
The state is going to be defined by,
No, but without that.
suppose there is no constraint.
No constraint.
There is no, the state is existing. The memoryless.
But what is that symbol? What do you?
It can be anything. You can just define certain state and the channel always stays in it. You can say there's no state, you can say there's one state and the channel remains there.
Can we give this analogy? So in case of fading channel, why is the matrix percent?
Sure, yeah. So that is one. Yeah, so for example, for a fading or what we call an ISI channel, suppose you have summation HIX I minus K, okay, that K runs from 0 to n. The memory of the channel, the number of states of this channel is going to be like 2 power n. Sorry, yeah, the number of states is 2 power n, the memory of the channel is.
But even if it is not summation, right? If it is only one pattern, that
Yeah,
is also the random variable. So that
Gives you 2 states.
the set which we states. Okay.
Correct?
And the set from which the fading coefficient takes the value will be the overall states.
Yeah, sure.
And if we say that it is a deterministic channel, like this H is not time value, then we can say it is, as you said, the state is
Yeah. So I was assuming that the state was deterministic. In the event that you don't have this sort of frequency selective, I'm assuming of this. Okay, so again, coming to Professor Parimal's point about what is the main idea here. So the main idea is to utilize codes that do well over memoryless channels and adapt them to channels to the setting of input constraint channels. That is all that there is. So in particular, there are very well-known linear codes that perform well over these channels. Okay, why is linearity important here? It's important because if you have a linear code, then subcodes of the linear code will also have the same average probability of error under the same decoding procedure. So in particular, if your linear code is capacity achieving over a particular channel, any subcode of the code is also going to have zero error probability in the limit as blocking position. Okay. So our only idea is you pick a good linear code and look at constraint subcodes of it. In particular, we'll be looking at Reed-Muller codes, which are codes obtained via polynomial evaluations. And these are codes that have very recently been proved to be capacity achieving over any VMs. And we'll try to obtain estimates of the rates of the constraints. So in this,
you do want to find capacity, but you do not know. Right? You're saying that I can find one code whose subcode has this input constraint property, and this is achievable rate. I mean, giving this thing, right? You're hoping that what best case scenario is capacity, right?
it's not. It is the kinds of rates that we can calculate are not close to the capacity.
Oh, so you know the capacity.
We know upper bounds on the capacity.
Actually, but you do not know how close it is. Right?
We know that they are fairly close because we can numerically compute lower bounds, not via these kinds of things, via random coding algorithms
Okay.
that are close to the upper bound. So we know the gap, the sort of.
And you are far away from that? Or?
We are not far away from it. It depends on what your goal is. If you want to reach the sort of numerically achievable bounds, then yes, we are far away. But there are even probabilistic arguments that you can make using linear codes. So if you look at random linear codes, for example, what can you do using that? For certain kinds of constraints, we are actually able to beat this. That is. Okay. So let's look at what we can do using Reed-Muller. So what is the constraint that we'll be looking at? It's a certain kind of a runlength-limited constraint. This is the so-called D-infinity runlength-limited constraint. What this means is that your input sequence must be such that there are at least D zeros between every pair of signals. For example, when D equals 2, this sequence here does affect the constraint, whereas this sequence here does not affect. And these are constraints that have been traditionally used for IISc alleviation in magnetic recording, simply because it ensures that the voltage peaks, which correspond to ones, are sufficiently far away. Now, there's a lot of work on this runlength-limited channel models in the context of computation of rates, bounds on capacities, and so on. And possibly the only work that looks at constructing codes over such channels is the work of Kadaput and Kumar about 30 years ago. which gave a very simple existential lower bound on the rates achievable over such channels. Okay. But on the information theoretic end, we do have a long line of work, beginning with say Jahavi and Kaufman, who provided random coding arguments and computable weights using these random Markovian input distributions. And you can use the same random Markovian input distribution and generate even better algorithms, like stochastic approximation algorithms, quantifier schemes, in order for computing achievements. And from the other side, you have upper bounds on the capacities of these channels, and these are derived using well-known methods in information theory, the so-called dual capacity methods. So how does this talk fit into the picture? Well, we are providing explicit codes over such channels. We're telling you what codes you can use and what their rates are, and their corresponding decoding algorithms. Now, one caveat here, I will not be speaking about the proofs anywhere. I'll just be giving you a sketch of the results, at least for this part. We'll be using our learnings from here in order to develop more things.
So one clarification, the code word needs to have that being not the message.
No, not so. The message, according to me, is just a symbol that takes values from 1 to 2 to the end.
The code word needs.
Yeah, the code word needs 2. Yeah, that is fair.
And we look at the case where the input itself has a constraint, like the message itself has.
The message is just a number between 1 and.
So you haven't looked at that case, but the message itself is constrained.
Oh no. Yeah. Okay, so like you pointed out, the code words must respect this. Code words are binary sequences that must respect this. So what are Reed-Muller codes? Reed-Muller codes are obtained by polynomial evaluations roughly. So if you look at a Boolean polynomial f that takes values from Boolean range from the polynomial ring, and let us denote by eval z of f to be basically f of z. So we have a point z and we evaluate f at that point, you get eval z. Now let us assume that the points, the 2 power m points corresponding to binary sequences of length m are arranged in this kind of a fashion. Okay, so this is the standard lexicographic order. Now a Reed-Muller code basically consists of vectors that are the evaluations of such Boolean polynomials at these 2 power n points in this order. Right? And what is that specific collection? Yeah. So more specifically, the rth order Reed-Muller code Rn and R is going to consist of the evaluation vectors of all those polynomials of degree at most R. Okay. So the degree of any Boolean polynomial is basically the degree, the largest degree of any polynomial is present. And we restrict that largest degree to be at most. So that is basically the definition of Rn. Alright. So a few more facts. When the dimension of this is a linear code firstly. Okay, so that is easy to verify. And the dimension of this linear code is basically the number of monomials of degree at most. Okay, and that is m choose less than equal to r, and that gives us the rate of this Reed-Muller code. Okay, because there are 2 power m points that you're evaluating based on, and there is a. Now, what is key here is that given any particular rate capital R that you want to design codes for, you can always construct a sequence of Reed-Muller codes whose rate is capital R. Okay, and this is a very canonical construction that has been used in literature. This will appear again sometime. So you can verify that the rate of this sequence of Reed-Muller codes, that is the limit of this quantity as n goes to infinity, is in fact when Rn is just. So what do our results firstly look like? I'm just going to flash some of our results at you, and we'll see what we can say about more general constraints. Firstly, we can identify linear constraint codes, subcodes of Reed-Muller codes, and the rate of these linear constraint codes is r times 2 to the minus log d plus. So again, we start with a Reed-Muller code of rate capital R, and we are able to identify linear subcodes of this Reed-Muller code. Okay, so emphasis on the word linear, and the rate of these linear subcodes is so much. Now, just to these things out, 2 to the minus log d plus 1 is roughly 1 by d plus 1. Okay. So you can basically achieve a rate of r by d plus 1 using these subcodes. And what do these subcodes look like? For example, when d equals 1, these subcodes are basically all the symbols in their odd position. But what is the best that we can do using linear subcodes? Well, for example, if you choose any which sequence of Reed-Muller codes, not just the sequence that you're working, it is possible using some arguments to show that the rate of any linear d infinity order subcodes of these codes is at most r over d plus 1. Okay, so in particular, what this means is that last time we identified linear subcodes operate so much, this is roughly r by d plus 1. The maximum rate you can achieve is again r by d plus 1. So our linear subcodes are essentially rate. Okay, but what more can we say? Well, if you look at the constraint, the thing is, if you reorder the coordinates of the Reed-Muller code, then you can basically take a code word that doesn't respect the constraint into a code word that does respect the constraint. Okay. And we say that under pretty much all coordinate ordering, so long as the block length is large enough, the rate of the largest linear subcode, which is also d infinity r compliant, is at most r by d plus 1 plus some small percent. Okay, so basically, if you want to look at linear subcodes of Reed-Muller codes, you can't do better than r by d plus 1 plus. But let us allow for a larger search area. Suppose we ask for what is the rate that is achievable using non-linear subcodes. Well, in this case, for certain specific values of d, for example, when d equals 1, we can show that a rate of r minus 3 over 8 is in fact achievable. Okay. And in particular, this is better than the rate of r over 2 that we got using linear subcodes. Right, this is all dry talk. So let us look at pictures to see how this compares with known results. The black line that you see here is what is called the coset averaging lower bound. It's basically the simple existential lower bound, which tells you that there must exist some coset of any linear code which has at least so much rate of d infinity r sub. Okay. So how is this lower bound obtained? It's a very simple argument. You look at the set of all constraint sequences. Okay, there are let us call this set as having some cardinality A. Now you have a linear code that's given to you, and it's going to have a certain number of cosets, right? So let us divide the total number of sequences, the total number of constraint sequences cardinality of A, by the total number of cosets. This is basically going to give us the average number of constraint code words in any coset. Right? And by the simple argument that max is larger than equal to average, there must exist some coset which with at least so many constraint code words. Okay. Now, this is very similar to an argument made using the probabilistic method. So basically, just to translate it in the language of probability, suppose you have a random linear code, and you look at a constraint subcode which also respects this constraint. Then this constraint subcode is going to have rate exactly whatever is given by this coset averaging. And these kinds of probabilistic arguments are very hard to beat using explicit constraints. It requires a lot of very specific work to be done in order to beat probabilistic arguments. There's a caveat that I wish to emphasize. So fine. So you have this kind of a probabilistic lower bound that's given by the black line, and the blue line is whatever we can construct using explicit subcodes of Reed-Muller. This is actually very simple. I mean, in the area in which the blue line beats the black line, it's actually a pretty simple construct. But the point of worry is that we are not doing very well in the limit as the rate goes to 1. Okay, so that's another point that we wish to address. And we address it via this kind of a concatenated coding scheme. And the idea behind the coding scheme is goes back a long way to early work on constraint coding. Okay. And it's attributed to Bliss and Mansouri. The idea goes as follows. Well, suppose I have a message queue. You can think of this message as taking one of Kupar and our many values. And I wish to come up with a constraint sequence that I want to send over the channel. So I first encode it via a constraint encoder. it gives me some sequence that is also constrained. And I want to introduce error correction, right? I want to correct the kinds of errors that the channel may use. So I have a systematic error correcting encoder here, uses parity bits, and I encode those parity bits again using the constraint engine. Okay, so there are many encoders here, and these are all put together and appended to get a final constraint sequence. So that is the simple idea behind the encoding part of the scheme. And what do? We just replace the systematic ACC encoder by systematic Reed-Muller. And we replace the second constraint encoder by a subcode that is also constrained of the Reed-Muller code that we had designed. Now, the interesting thing is we're actually introducing more error correction into the system than what was available via this construction. Okay, because here the constraint encoder doesn't really introduce any error correction. It doesn't have any error correction properties. But what is important in our proof is that this guy also is capable of correcting errors. And how do we decode? Well, we send the constraint code word over the channel, and then we try to invert whatever procedure we did for the input. It's part of it. So we do use certain very specific decoders which are mapped to their corresponding encoder blocks, and we are able to show that using this scheme, using a slight modification of this scheme, a rate of this complicated expressions in fact. Okay, so again, using rate R Reed-Muller codes, you can achieve a rate of at least so much using this concatenated coding. Right? Just to demystify certain terms, the C0 T here is the so-called noiseless capacity of the constraint, which is basically the rate of the constraint sequence in the limit as a block. Okay, again, to see in pictures what this looks like. The red line here shows whatever rate is achievable using this concatenated coding construction. And you can see that it significantly less the linear code that the linear codes that we were working with earlier. And in particular, we are able to get very close to the so-called noiseless capacity in the limit as R goes to. Okay. Another fact that we wish to emphasize is that we really haven't done much better than the probabilistic lower bound even here. And in the second part of this talk, we'll actually be seeing certain very special constraints are being able to beat this lower bound. All right, so before I conclude part 1A, there are some open questions here. These are very broad open questions. So one is, everything that we have done here depends on good bounds on the weight distributions of Reed-Muller. And this is a huge open problem. We do have some bounds on weight distributions of Reed-Muller code also, but they're asymptotically not much better than the existing. Secondly, can we use the kinds of techniques that we used here over other channel models like the Gilbert-Elliott channel, for example, or for other IISc models? Because Reed-Muller codes, at least for polar codes, are known to perform very well over these channels with memory. Even there are no explicit constructions, there are just existential proofs. But can we explicitly construct code using Reed-Muller or polar codes to do that? So let us go to part 1B. And
So essentially, you're able to find the codes that satisfy those constraints. That is, the code word is rich enough, right? So there are multiple code words and that's it. So is that true for any linear code, or is it something special to the Reed-Muller codes?
It's true for any linear. But of course, you want to use linear codes that achieve capacity over the unconstrained channels. And then you're going to have some property of error guarantees for these.
So in that sense, Reed-Muller code is better than the codes. That's why.
Yeah. So in the sense that Reed-Muller code has more structure than most other capacity achieving constructions. For example, if you look at polar codes, they have an underlying choice of these bit channels. Okay, so that needs to be fully understood before we can construct such coding schemes over using polar codes. The same holds for LDPC code. There's an element of randomness. Okay, so these guys are algebraic codes with structure, which allow us to construct explicit.
So in some sense, it's possible to find some other linear code that performs better than code.
Yes, sure. So that is completely open. But our belief is that unless we have more knowledge about, unless we make these other constructions more explicit in certain very precise ways, like polar codes, you want to know what these bit channels are that you're using. So in that case, for certain very specific channel models, like the BEC, for example, you can construct codes that perform as well. That is something that we have been able to do. Sure, it's still open, to PPs.
And one question, so there might exist multiple subcodes that satisfy the constraint. So which one do you pick for
The
largest? That's
the only thing. So that's the main reason why we use linear codes. You can use any subcode. It need not be linear anything. There needs to be no further structure to that subcode besides the fact that it's constrained.
And the reason for choosing the largest is
Great.
that is the notation.
That
Increase the length, then the rate increases.
increase the size.
Size. Yeah, sorry, size.
So that is the point of view that we are adopting in this part. Basically, if somebody gives you any bits linear code and any bits constraint, can we say something about the size of the largest constraints? We saw a potential application for that in part 1A. But let's try to address this question provided that it is. So you have a linear code here, C, and you want to count the number of constraint code words that are present in that. This problem, we approach it from an angle that hasn't been viewed from in the entire history of constraint coding for some weird reason. So the argument is very simple. So what do you want to count? You want to count the number of constraint code words in a linear. Write that number as this kind of a sum of indicator functions. Okay. The sum over code words of the code of the indicator that the code word also complies with the constraint. Now I just write the same thing differently as the sum over all words of length n of the product that the word both lies in the code and satisfies. What does this help us to do? Well, this looks like an inner product between Boolean functions. Okay. So let us try to see if we can use some of the language of Boolean functional analysis to do this. Just a brief refresher before that. There may be people more well versed in harmonic analysis, so let me just go through this quickly. So given a function f that's defined on the hypercube, on the hypercube 0, 1 to the n, you define the Fourier coefficient f hat at the point s that way. Okay. It's basically the sum of f of x times minus 1 to the x dot s, but normalized. And given any two functions that are defined on the hypercube, we also define an inner product between them as follows. So the inner product between two such functions f and g is this the sum of f of x times g of x, but scaled by some constant 1 by 2. And the only thing we're going to use is a very simple idea from the first chapter of any book on Boolean functional analysis, Rameshwar theorem. And it basically says that this inner product can also be expressed as the sum of products of Fourier. Okay. More precisely, we want to compute that inner product there. So using Rameshwar's theorem, it can be written again as this. It's 2 power n times the sum of products of Fourier coefficients. Now for any linear code, it is possible to simplify the Fourier coefficient indicator C hat. Okay, so in particular, indicator C hat, where C is linear, is in fact indicator C per. Okay, so the indicator of the dual code, but normalized by some. And this can be true. So in particular, what this means is that the number that we are trying to get at can actually be expressed as a normalized sum of Fourier coefficients. But when I say Fourier coefficient, I mean the Fourier coefficient of the indicator of the constraint. Okay. And this is something that is potentially useful for two reasons. Firstly, if your code is very large, if the dimension of the code is large, then you might as well use that formula to count over the dual code is not small. That is the first obvious plus point. The second is this is made evaluable by the fact that the Fourier coefficient that you want to compute is in fact computable for a large class. And this is a fact that we wish to emphasize here. And as future work, it's definitely quite interesting to explore Fourier coefficient independently. So this crops up in a large variety of problems. A large number of counting problems involving constraint codes can be solved using these Fourier coefficients, and it's of interest to try and completely evaluate these coefficients. Okay, so let's look at some simple examples. For example, when the constraint is just that your code words must be of a certain weight. So the channel only allows those constraint sequences, all of which have a certain weight. Then by a simple application of our Constant's work cost, you get this kind of a relationship. Okay, so what does this mean? It just tells you that the number of code words in a linear code of weight I is related in some way to the numbers of code words of different weights in the dual code. Okay, and this is a very, very well-known relationship in coding theory. These are called the Macdillion's identities. And in fact, this is really the proof of the Macdillion for linear. So let's go to a slightly more non-trivial example. Let's look at a charge constraint. So these are constraints that basically require that the running sums of the sequences must not exceed a certain threshold and must not lie below certain. Really, the sequences that we'll be working with are sequences that can be read off parts of the screen. So for this constraint, actually, just to spare you the details, we've been able to fully characterize the Fourier coefficients. In particular, we show that there exists some vector space, and only if the point S lies inside that vector space is your Fourier coefficient going to be non-zero. Outside that vector space, your Fourier coefficient is going to be zero. Okay, this is slightly different from the case with the subspaces themselves. I mean, this constraint is not linear. This is a non-linear constraint, but it has very nice looking Fourier coefficients. Okay. So we derive a lot of consequences of that can be talked about using these Fourier coefficients. Well, firstly, we can get conditions for the positivity of the number of code words that follow the respective constraint in any given field. Okay. So the condition looks something like the Fourier coefficient. Okay, this can be made more explicit, but roughly speaking, the dual code must have significant intersection with a positive value Fourier coefficients. That is the broad idea. But in such a case, you can not just say that the number of constraint code words in your linear code is non-zero. You can also completely count the exact number of constraint code words that are present. Okay, all these are just simple consequences of the fact that the Fourier coefficients are counted. Okay. In particular, what this means is that we are able to explicitly identify subcodes of linear codes, and these subcodes are also constrained. These subcodes are not linear, and the rate of these subcodes, which is r minus half plus something, beats the Gaussian averaging rule. Okay, so this was a probabilistic argument that we were alluding to earlier, and we are able to explicitly identify linear codes whose subcodes have rate that can potentially be better than this probabilistic for this specific constraint. All right. But what's more is that we can actually apply our arguments to specific linear codes, to well-known linear codes, and completely characterize the number of constraint code words. Okay. Either analytically, for say the Hamming family, or numerically for the Reed-Muller codes. Okay, so note that these are very high rate, large block and Reed-Muller codes. It's hard to count the number of constraint code words directly, numerically. But using this simple Constrained argument, you can convert it to a question about the structure of the dual code and count well there. To give you one final example, so let's go back to this infinity arbitral constraint that we were speaking about, where any sequence must have at least d zeros between register ones. For this constraint, we are able to derive a recurrence relation, okay, which allows for the efficient computability of these Fourier coefficients. Okay. The exact form of this recurrence relation is not important, but the important fact is that if you were to build an algorithm based on these recurrence relations, then this algorithm is much faster than the fast Gaussian transform, which is the fastest way of computing generative Fourier. Okay. So there's a lot of potential here. We also do have some knowledge of what these recurrence relations should look like for general constraints, but we haven't proved them yet. So this is a very interesting problem for future research. So we do have some similar such computations made for subdot constraints also, and we compute the number of constraint subcodes of Reed-Muller codes using this formulation. And all of this is in our reason. So let's go to some questions that are left open by this. So the first one has been dealt with by us. So can we design these kinds of recurrence relations for general constraints? Secondly, can we say something about the asymptotic rates of the constraint subcodes of general linear codes? If somebody gives you a linear code, what is the asymptotic rate of the constraint subcodes within this linear? And secondly, are there more use cases of the Fourier analytic approach that we just outlined here? One very simple use case is that we can also compute weight distributions of constraint code words using this kind of an approach. That is also something that we have done. But there are more interesting use cases, we are sure. It's just that we don't know where these things can be.
So, how do you find the subcode? The basic process of finding that subcode that satisfies.
Yeah, so for example, so the structure of the Fourier coefficients directly will inform the structure of the subcodes. We tell you which subcode is there. It's so for example, for this,
Just for counting the number of code words.
this is not just a count. So if you can completely characterize the Fourier coefficients, you can look at what the dual code must look like in order for your primal code to have a certain number of constraint codes. So in that sense, you are designing your linear codes.
Is there any principled way to?
Yeah, so that is, we are doing it for very specific constraints in very ad hoc ways that are specific to each of those constraints. There is no principled way as of now, but that is something that we wish to explore. Also, using these kinds of recurrence relations, try and see if there is some more structure to these Fourier coefficients that allows us to identify these things.
How many supports are there?
Yeah. So that is also there. We are interested in the largest subcode, largest constraint subcode.
But are there infinite supports or are there finite supports that satisfy the constraint?
Oh, that, yeah. I mean, given block length, the code size is finite. So there will be finite images. We're looking at finite block length cases here and then taking the limit test.
The previous thing that you presented, so those results are only for that D-infinity constraint?
Yeah, those are only for the D-infinity constraint. Certain things can be ported to other constraints also. But they sort of don't give you great results. They just tell you things that you might already know about these constraints. So yeah, and we believe that this is a much better way to tackle such problems using this Fourier analytic approach instead of just brute forcing it through the coding theory. Fine. So we come to the last part of this talk, which is going to be on a completely different thing. So until now, we were concerned with the construction of coding schemes over random noise channels. And now we're going to change the channel model and say, suppose you have an adversarial channel which can introduce errors adversarially. That is, the channel can puncture, code symbols with potential knowledge of the code word itself, but it only has an upper bound on the number of errors that it can introduce. Now, for this kind of setting, what we are trying to do is derive upper bounds on the sizes of constraint codes with a given error. So again, you have this kind of a channel model. You have a constraint encoder. You have a channel that introduces adversarial errors. And our task is to recover whatever code word we send with zero error. Right? And basic coding theory courses tell us that essentially what we're looking for is some sort of relationship between the size of the constraint code and its minimum values. Okay, so this is a very coding theoretic point of view, constructing constraint. Okay. So to distill the problem again from this channel model, you have a hypercube like what is shown here. This is shown in 3 dimensions. It is not the right picture that you have in mind. If you guys are capable of imagining n dimensional, that is the thing. So in an n-dimensional hypercube, suppose you have a constraint that is given to you. What is the largest number of points of this n-dimensional hypercube that you can pick, so that this collection of points has minimum distance? Okay, so this is a very, very standard question in any coding theory course without the constraint. Okay, and all of us know that there are like these upper bounds, Hamming bounds, sphere packing bound, Plotkin bound, singleton, and whatnot for upper bounding the sizes of codes with a given minimum Hamming distance. Now let us see what happens when we introduce this. Okay. Now the state of the art as far as this is concerned are what are called the generalized sphere packing bounds. They are fairly recent as far as the constraint coding is concerned. They go back 7 years, 7 years. So the question is, can we test these bounds? Can we build these? So let's just refresh something that is very, I mean, the coding theorists know about a lot, but it's not really covered in a first course in coding theory. So these are called the Delts. This is called Delts linear program for providing upper bounds on the sizes of codes with a given minimums. And the linear program goes something like this. You have n+1 variables. Okay, so these are called AWs, A1, A0, A1, A2 till AN. And they must respect certain constraints. These are linear constraints. And so the entire thing is a linear program. Okay. In particular, these guys must be positive, must be non-negative. There is some other weird looking constraint here, which uses something called Round-trip polynomial, coefficients of Round-trip polynomial. And this is something that we actually saw earlier, may not be fresh in memory. And then there are some other constraints related to the variables that are present. And importantly, Delts not just set up this LP. I mean, he did a lot of work related to what are called association schemes in coding theory, which is an extension of association schemes from statistics to the language of coding. But anyway, he set up this LP and then showed that the distance distribution. What is the distance distribution of a code? It's basically the average number of pairs of code words of distance I. Okay, so if you have a given distance I, Bi is basically going to be the average number of pairs of code words that are at a distance I. And putting all the Bi's together is going to give you the distance. So Delts showed that the distance distribution BW actually satisfies this linear program. Okay. In particular, this provides a feasible solution to this linear program, and hence its value, the value of this feasible solution, is a lower bound on the value of the linear program. Okay. Or in other words, the value of the linear program is an upper bound on the value of this feasible solution. What is the value of this feasible solution? It is just the size of the code. Okay. So in other words, the value of the linear program is an upper bound on the value of the feasible solution, that is the size. Okay. So the largest possible code of minimum distance at least D and of clock length n is upper bounded by the value.
This is the value K which we can take.
KWJs are integers. They can even be negative. They are off the cuff. It's difficult for me to. I mean, I think K0 of J for any J is 1.
So they can take arbitrary values.
No. It's an integer. Like KW is a polynomial. It's a known polynomial, and we're evaluating the polynomial at the value.
What is the meaning of this constraint? Like you had some explanation of dual code and stuff. Like what does it mean?
Here, no dual code. Nothing. The code is not even linear. It's just any which code.
So this AJ KWJ is no meaning. It must have some constraint.
This has no meaning. So if you don't look at it without this kind of a feasible solution in place, it's just some arbitrary linear.
So for the feasible solution, what does that mean? That constraint.
Which
But if you put AGS degree distribution of a binary and then 4,
yeah,
then what does that constraint mean?
this constraint.
Yeah.
It basically means that the distance distribution of the dual code must be positive. Must be non.
Can we see this integer programming?
This is not an integer programming problem. I have not restricted the AWs to take on integer
It
values.
is only as for this, it is 0. That's what saying AW is 0 and okay.
Only for special value.
It is, otherwise, it can't be any value.
It can. It is just a linear program. You can do what it wants, but yeah, preferably these values should be integral. Even if they're not integral, you can round the final optimal solution to get enough problems. Integer linear programs are very hard to solve. They're NP hard. So we relax them and okay. So let's take a step back and look at the same program a little differently. I claim that this kind of a linear program stated this way is exactly the same linear program that we saw earlier. So this is another fancy looking program. It has a much larger number of variables. It has 2 power n many variables. And the variable here is basically f of x for all x. So there are 2 power n many variables there. And there are some constraints here. Okay, so here you have the Fourier coefficients and so on. This is something that we saw even earlier. Okay. So you can construct a feasible solution for this linear program also. Using, okay, you can construct a feasible solution and then again show that the value of the feasible solution is again the size of the code. Okay. So again, this linear program, its value is also going to be an upper bound on the size of the largest code with a given meaning. In fact, there is more to be said. These two linear programs are equivalent in a very specific sense. It's not just that their values are the same. It's also that any feasible solution of the first linear program can be translated to a feasible solution. Okay, but let's just forget all of that and let's just work with this guy and introduce one further constraint. So that is all that we are going to do. So suppose somebody asks you now, I'm going to give you a constraint being not LP constraint, the constraints that we were working with. So the constraint is represented by set A of constraint sequences. Now I just define a linear program this way, with the final LP constraint being something that is like this. Okay, so this guy here is a convolution. So using this new linear program, I'm not going to go into the details because we can again get an upper bound on the square of the size of the largest code that also respects the constraint and has a given numerically. Okay. So just to show you some numbers, we ran this for the D infinity arbitral constraint. For many constraints, we actually ran that. I'm just showing you on two such things. What you see in blue here is the state of the art. These are the best known upper bounds on sizes of codes with a given minimum. And these are whatever we get using our linear. So clearly, our linear program is much better than the same way when D. Alright. Now there are many small things that we still need to address. For example, in our work, we have been able to reduce the size of this linear program greatly. I told you that there are 2 power n many variables. Now, for different constraints, we have been able to reduce the size of the linear program using a synchronization technique that makes use of the automorphism constraint. We have also been able to show that our linear program satisfies some really sanity checks. Some sanity checks that must be satisfied. For example, our upper bound is at most the upper bound that Delts LP gives you without any constraint. It is also upper bounded by the number of constraints. Okay, so it's not a stupid linear program, it really does whatever it's supposed to. And finally, we want to take this further and then we want to apply known Fourier-analytic techniques or expansion graph based techniques in order to derive asymptotic great distance trade off upper bounds using this. So that really are the questions that we need to deal with in future work. Thank you. Are there any questions?
Yeah, just one question. We were teaching limit This block. So if you want finite block length counts, so in this method, we use there or we use
The Fourier-analytic thing will give you only finite block length counts in first year. We are taking the limit so as to get some asymptotic rate guarantees. But the first kind of approach is not going to give you good finite block length. I mean, the first ad hoc coding theoretical approach. Finite block lengths, not much can be said. In the limit things will be said.
in one way, if we can give some stochastic representation of the same channel model and then use the traditional block length to get to where how far you are.
Yeah. So that is definitely those. I have not shown you those plots. So yeah, using random coding such arguments, you can get bound very close to capacity input. That was what Arvind was asking. So those are how are those things derived when you just take your input distribution to look like the finite state machine that it's a constraint. So if your input distribution looks that way, it's Markovian in a certain sense. Then you can numerically derive algorithms, stochastic approximation schemes that will give you rate guarantees, numerical rate guarantees.
Thank you, Arvind, for that informative talk. We would like to remind our audience to please subscribe to our Google Groups, which is the mailing list for information on our future talks. You can also visit our website for more details. And the link to the video and the slides will be updated on the webpage. Thank you. Have a great evening. In-person audience, please, you can please join us for some coffee and refreshments at the coffee. Thank you.